Hello and welcome to this presentation related to friction belt drives. This is part 2 in the lecture series. In this presentation we're going to consider centripetal effects associated with flat belts. In the previous presentation we introduced friction belt drives, outlined the characteristics, the terminology and the nomenclature used in the analysis of friction belt drives. We derived the formula for power transmitted by a flat belt drive, and undertook some examples which illustrated the use of the various equations that were stated and derived in part 1 of the presentation. Here's a presentation overview of the friction belt drives part 2 lecture. We're considering flat belts but with centripetal effects. The presentation commences with a review of the underpinning knowledge related to mathematics. This knowledge will help you understand the derivations we're going to review in the presentation, and also underpinning knowledge related to mechanical principles, for example Newton's laws of motion, friction forces, centripetal forces, etc. Next there is a recap of centripetal force and also the centrifugal force concept. The presentation then considers the analysis of flat belt drives, but this time, but unlike the previous presentation, we're now going to consider the centripetal effects. This is the equation we would derive from the analysis. We consider an analysis of power transmitted when centripetal effects are considered. And here's the equation for power transmitted from our analysis. And example 3 calculates the power, P, that can be transmitted given stated parameters of our belt drive system. Example 4, we calculate the power that can be transmitted given stated parameters for our belt drive system, and we also consider the condition for absolute maximum power and the parameters required to achieve this essentially theoretical condition. This condition is graphically shown through the solution for example 4. We next show the maximum power transmission analytical proof that confirms the results found in example 4. And here's the equation for the theoretical maximum power that can be transmitted. And finally, and purely for reference, we consider the design requirements associated with the installation of friction belt drives. And for reference, here are the start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation. But please note these are only approximate start times. For reference, here's some underpinning knowledge that's required to aid your understanding of this presentation. This slide relates to engineering mathematics knowledge. We will make reference to radian measure, the S equals to our theta formula during our derivations. Note the radian measure formula relates to our sector of a circle here, where S is the arc length, R is the radius, and theta is the angle subtended in radians. We need to be aware of integration using standard forms, such as that shown in the standard integral table from our previous set of notes, and the ax to the n format, the polynomial form, and also integration using substitution. We need to be aware of natural logarithms, the ln function, and exponential functions, the e to the x function. Also, we were required to differentiate expressions using standard forms, ax to the n format, again the polynomial form shown here in our table of standard differentials. We will also reference differentiation to find turning points. Find the first order differential equation dy by dx, and then the second order differential equation d2y by dx squared. And finally, as with all derivations, there will be a requirement to transpose equations, rearrange equations. So that's some of the underpinning mathematical knowledge we'll require to understand the derivations in this presentation. For reference, there are separate presentations related to all these engineering mathematics topic areas. There's also an array of underpinning mechanical principles knowledge required. we need to be aware of Newton's laws of motion. The first law, written the summation of all the forces on the body equates to 0. And the second law, summation of all the forces equals to mass times acceleration. We need to be aware of the relationship between linear and angular motion. In other words, relationship between linear velocity and angular velocity from the v is equal to omega r equation. We need to be aware of centripetal acceleration. A is equal to v squared divided by r. And the associated centripetal force, F equals to mv squared upon r. Remember from our previous presentation on circular motion, we need centripetal force to keep a body or mass rotating a constant radius, circular motion here. And we'll also refer to D'Alembert's principle, the concept of centrifugal force, which is considered to be the equal and opposite force to the centripetal force. We'll also make reference to the basic friction model, where the friction force, Ff, is equal to the coefficient of friction, symbol mu, multiplied by the normal force, the reaction from the surface on our body. There are separate presentations on all these mechanical principles topic areas should you wish to revisit and review the various topics. Just a very brief recap on centripetal and centrifugal forces from our previous presentation. The centripetal force is the force required for motion in a circular path of a mass, labeled m here, at some radius r from center of rotation. If we consider our mass rotating against our inertial axes, fixed to the ground in most cases, then we can simply apply Newton's second law as it's written as summation of all the forces equals to mass multiplied by acceleration, where the centripetal acceleration A can be written as the angular velocity omega squared multiplied by the radius r, or it can be written as the linear velocity v squared divided by r. However, if we now consider what is termed body fixed axes, so now the axis set we're using is located on the body and moving with the body, we will still have our centripetal force acting inwards to generate the circular motion. We have to introduce what is termed an inertial force. For rotating masses, this is called the centrifugal force, which is sometimes also referred to as a compensating force or a fictitious force acting outwards, which is considered equal and opposite to the centripetal force. We now have to write Newton's second law in the form of summation of all the forces minus the inertial force ma, the centrifugal force in this case, is equal to 0. That's D'Alembert's principle, which we reviewed in a previous presentation. Essentially, D'Alembert's principle allows a dynamic situation to be analysed statically. So just for reference, we will use the centripetal force to derive the various formulae within this presentation that will be used to calculate the power transmitted, etc. in the various questions. But when referring to various textbooks, sometimes the centrifugal force concept is used to derive the equations. So for the purpose of this presentation, we're essentially using the terminology interchangeably. So where questions state consider the centrifugal effects within our friction belt drives, they are essentially referring to belt drives rotating at high angular velocities, where the centripetal forces required detract from the driving tensions within the belt. So just be aware of that terminology as the presentation unfolds. And purely for illustration here, I found these pictures, although I cannot remember the reference source now, related to friction belt drives. And this first picture shows the belt with negligible centrifugal effects to consider. So this is essentially a belt rotating at low angular velocities, low speeds. And the centripetal or the centrifugal effects are negligible. And here's a picture of a friction belt drive where the CF effects are considered. We can quite clearly see that the belt here is lifting off of the lower pulley due to the high rotational velocities involved. Again, my apologies, I do not have the reference source for these pictures. So centrifugal or centripetal tension, labelled as TC in our notes that follow, has the effect of reducing the tension available for transmitting power in our friction belt drive. And later you'll see we derive the equation for centripetal or centrifugal tension in a belt as mv squared, where m is defined as the mass per unit length of the belt, usually kilograms per meter, and v is the linear velocity of the belt in meters per second. And for reference, it's clear why engineers quite like the centrifugal force concept, because you can imagine the centrifugal force pulling the belt outward away from the pulley as the speed of the pulley increases. So as I say, a useful concept to use is centrifugal force. Let's consider the analysis of belt drives, this time considering centripetal effects. So when a belt transmits power to a pulley, there is a difference in tension between the tight and the slack sides of the belt due to the friction force between the belt and the pulley. For the flat belt section shown in figure 4, here's figure 4 here, having an angle of lap theta, which is about to slip in the direction of the motion. Direction of the motion shown here, labelled as omega. The total tight and slack side tensions, denoted as TT, shown here, and TS, shown here, are characteristics of a belt drive when rotating. The belt has a mass, symbol m, per unit length. In SI units that would be kilograms per meter. Let's now consider a small arc, shown here in the sketch, figure 4, and this small arc subtends angle d theta, labelled here. Although angle d theta looks quite large in figure 4, try and conceive of angle d theta as being so small that it cannot actually be measured. So a very, very small angle, very, very small slither of belt we're considering here. If we let capital T be the tension on the left hand side of our elemental strip and T plus dt be the force on the right hand side of our elemental strip, then these are essentially the tensions in our element, the left and right hand side. Note that force R, shown here, is the force applied from the pulley on the belt as the belt rotates around the pulley. So R is the radial force between the pulley and the belt. Here's our analysis of belt drives continued. I just tried to show here an enlarged view of the elemental strips, shown shaded in yellow here. And this elemental strip, which is basically an arc of a circle, subtends angle d theta, shown here. So half the angle d theta is d theta upon 2, shown here and here. And note on the left hand side of our elemental strip we have tension T, and on the right hand side of the elemental strip we have T plus dt. Note that both T and T plus dt have an angle of d theta upon 2 to the horizontal, shown here on the left hand side force. R is our radial force, that's the force from the pulley on the belt. And note the force mu r is the frictional force generated by the belt due to contact with the pulley. And that's shown in this sense here, because our angular velocity is in this sense shown here. Analysis of belt drives continued. Now note as the belt travels in a circular motion, it must be subject to a centripetal, that's an inward seeking acceleration. We reviewed centripetal accelerations in a previous presentation. In that presentation, we proved that the centripetal acceleration A is equal to v squared divided by r, where v is the linear velocity of the belt in this case, and r is the radius of the pulley. So note, as an acceleration is present in the analysis, then we need to apply Newton's second law to this problem. So again, from a previous presentation related to Newton's laws of motion, the second law is written as the summation of all the forces acting on the body is equal to mass times acceleration. So let's firstly consider the radial force balance, and thus all the forces acting on the elemental strip in the radial sense. As always, when analysing forces, we need a sign convention because forces are vector properties. And note, in this case, the positive direction for the radial forces are downwards. So all we're going to do now is consider the forces applied to our small elemental strip, shown shaded in the sketch here. So summating all the forces in the radial sense, as the vertical sense here, first force I have is T plus dt multiplied by the sine of angle d theta upon 2. So in other words, that's this force component here acting downwards, so it's in the positive sense. And I've added to that the T sine d theta upon 2 force, which will be this force here. And again, that's downwards, so that's in the positive sense. And the only other radial force I have in this particular case is force R from the pulley on the belt as the belt passes around the pulley. And we minus the R in our equation because that's in the opposite sense to the positive notation we've used here. That's all the forces added up, and that equals to mass times acceleration, so capital M here for the mass, and the acceleration A. Just note in this case that the mass can be written as the mass per meter multiplied by r d theta, as already stated, the acceleration, the inward seeking centripetal acceleration, can be written as v squared divided by r. And just note from our previous presentation related to radian measure, to determine the arc lengths here, knowing the radius and the angle subtended, when using radian measure, the arc length is r multiplied by d theta. So that's where this value here is determined. So now considering the next line of the equation, just expanding the bracket. For the first term, we have t multiplied by sine of d theta divided by 2 plus dt multiplied by sine of d theta divided by 2. We still plus the t sine d theta divided by 2, and we still minus the r. On the left hand side, I now write the capital M for mass as m multiplied by r d theta, and the acceleration as v squared divided by r. And again, from previous work, for small angles stated in radians, sine of the angle is effectively the same as the angle itself. So we can now ignore the sine functions above. So these functions now can be ignored. So ignoring the sine functions and already having expanded the bracket, we now have t d theta divided by 2 plus dt multiplied by d theta divided by 2 plus t multiplied by d theta divided by 2 minus r is equal to our mass multiplied by acceleration on the right hand side. Again, from previous work, we know that we can ignore second order terms, in other words, very small quantities from our analysis without necessarily impacting on the final result. We need to be careful with that assumption, but generally speaking, that is considered to be true. And that allows us to simplify the expression as shown below. So we now have t d theta. In other words, we're adding this term and this term together. So that evaluates to t d theta. We're ignoring this term because we have dt multiplied by d theta upon 2, so a very small value the change in tension with a very small value change in angle and multiplied together is considered negligible. And all I've done is now added r to both sides of the equation. So that's why I've got a positive r on the right hand side. And I subtracted the MA term from the right hand side and brought it to the left hand side. So that's why it's been shown as negative on the left hand side. Just notice on the final line here on the slide, I've just turned the equation around here, so r is now on the left hand side. And note that I can factorize on d theta. I've got a d theta here and a d theta here. So d theta is the common factor. So on the right hand side, I have d theta outside of my bracket, and inside the bracket I have t minus mv squared. Notice also that the r's have cancelled, r in the numerator, r in the denominator, so I end up with simply mv squared in my final bracket. I've called that equation 9 purely for reference. Let's now consider the tangential forces acting on our elemental belt section. Note that the tangential forces must be in equilibrium because there is no acceleration in the tangential direction. So we will now apply Newton's first law to the tangential forces. In other words, summation of all the forces this time must equal to 0 for equilibrium. So again, repeating my diagram of my elemental strip here and the forces acting on the elemental strip. But now I'm considering the tangential forces. These are the forces in the horizontal direction acting on my elemental strip. Note also that for tangential equilibrium, we will have to consider the friction force. That's mu r, shown here. That's generated by the contact of the belt with the pulley. Positive notation this time of forces from left to right are positive. So consider our forces again. My first force, t plus dt multiplied by the cos of d theta divided by 2. That's this component here for this force in this direction. And I minus from that the t cos d theta divided by 2, which is this force in this direction going against our sign convention. I'm also minus the frictional force shown here, because that too has a direction against our positive notation. Notice it's drawn with a slight curvature in the sketch here, but of course because d theta is so small, then that is essentially a very, very small element, so that can be assumed to be a horizontal force. So the friction force is horizontal from right to left. And of course it has to equal to 0 for equilibrium, applying Newton's first law. What has happened on the next line is I simply expanded the first bracket for the first term. So we have t multiplied by cos of d theta divided by 2 plus dt multiplied by cos of d theta divided by 2. The rest of that line remains the same. Notice that we have a positive t cos d theta divided by 2 and a negative t cos d theta divided by 2. They obviously cancel. So on the left hand side, dt multiplied by cos d theta divided by 2. And all that's happened for the right hand side, I've simply added mu r to both sides of the equation. So it becomes positive on the right hand side. If we now make the assumption that cos d theta divided by 2 is approximately 1, don't forget from our cosine curve, cos of angle 0 would have a ratio of 1. So we can assume for very small angles used here in our analysis, cos d theta divided by 2 would be effectively 1. So this tends to 1. And dividing the equation throughout by mu, we can write the equation as r is equal to dt divided by mu. And I've called that equation 10. Analysis of our belt drives continued. Just repeated equation 9 and 10 for convenience here. So if we now equate equations 9 and 10, we have t minus mv squared multiplied by d theta on the left hand side, that's from equation 9, and dt divided by mu. Rearranging on the next line, we simply divided both sides of the equation by t minus mv squared in our bracket and multiplied both sides by mu. On the next line, we've brought the bracket of t minus mv squared to the top line and made it to the -1. And we're now going to integrate this function with respect to tension T between the limits of slack side tension Ts and tight side tension Tt. On the right hand side, we're simply integrating mu with respect to angle theta between the limits of 0 and theta, or angle of lap. On the left hand side, that's a non-standard form. So from our previous work, we're going to use the method of integration using substitution. So the left hand side integrates to ln of the t minus mv squared in the bracket between our limits of ts and tt. And on the right hand side, mu is a constant, so integrating a constant with respect to theta, we determine mu theta, and limits are between 0 and theta, the angle of lap. Analysis of belt drives continued. Just repeated this line from the previous slide for reference. If we now impose the limits of integration, on the left hand side the upper limit is tt, so we replace t with tt, and the lower limit is ts, so we replace again t with ts. On the right hand side the upper limit is theta, so we literally have mu theta, lower limit was 0. On the left hand side we've simplified the expression by applying the second law of logarithms. Here's the second law of logarithms, applied in this analysis from the right hand side to the left hand side. In other words, we're subtracting logs, these are natural logs here, so that's like dividing the brackets. So now we have just one natural log function, and in the curly brackets we have tt minus mv squared divided by ts minus mv squared, still equal to mu theta on the right hand side. If we now consider anti-natural logarithms of the left hand and right hand side, the left hand side of the equation simplifies to tt minus mv squared over ts minus mv squared. On the right hand side we have the exponential function raised to the power of mu theta. Again, we've reviewed the use of natural logarithms in a previous presentation. Note that the term mv squared is known as the centripetal, or sometimes referred to as the centrifugal, tension in the belt. And thus the centripetal or centrifugal tension, Tc, is simply written as Tc is equal to mv squared. Note that the m, of course, is the mass per unit length, usually kilograms per meter. Call that equation 11 for reference. Analysis continued here. So we can simply now rewrite this term on the left hand side of the equation in terms of Tc. So as shown here, we now have Tt minus Tc divided by Ts minus Tc is equal to e to the mu theta. Call that equation 12. Note that theta is the angle of lap of our smaller pulley. And just note for low velocities, the centripetal tension, Tc, is ignored. So equation 12 above simplifies to Tt divided by Ts is equal to e to the mu theta. Equation 13 for reference. So some useful relationships being derived here for us that we'll make use of when solving flat belt drive problems in later questions. Let's consider power transmission. So if the belt is used to transmit power between two pulleys of unequal diameter, the belt will slip first on the pulley with the smaller angle of lap. That's on this smaller pulley. If the belt moves with linear velocity v, then recalling equation 2 on our previous slide, repeated here for reference, and rearranging equation 12 to make Ts the subject, here's equation 12 from our previous slide, To make TS the subject, we will simply multiply both sides by this bracketed term here. We will divide both sides by e to the mu theta, and we will then add TC to both sides of the equation. So essentially TS is equal to TT minus TC, all divided by e to the mu theta, and then we add the centrifugal tension effect TC. If we now substitute this equation into equation 2, and just note for reference that e to the negative mu theta is the same as 1 upon e to the mu theta. We derive an equation for power P, and that's TT minus the TS as written above. So in other words, this whole expression here is now placed into here for this term TS, equation 2. We just remove the square bracket from this final line here. Power transmission equation from the previous slide. So noting that we can factorize on TT minus TC, it's a common factor here. We can write the power equation as TT minus TC multiplied by 1 minus e to the negative mu theta multiplied by V. So I said that's simply factorizing on TT minus TC in this line here. Call that equation 14 for reference. So that's now a formula for power transmitted when centripetal or centrifugal effects are considered. And again at low velocities, ignoring the centripetal tension effect, we ignore TC from the equation, so the equation for power simplifies to this expression here. That's equation 15 for reference. Again note that theta relates to the angle of lap on the smaller pulley, and that would be in radians, of course. So that's derived some useful equations in terms of relationships between the tight side and the slack side, tensions of our belt, and also the consideration of the centripetal or centrifugal effects and how that impacts on the power transmitted. Again, we'll be using these equations in later questions when we're solving problems associated with friction belt drives. Example 3. We're asked to determine the power that can be transmitted by a flat belt drive passing around a pulley of 1 meter diameter, which makes an angle of contact, that's the angle of lap, of 120 degrees if the speed of the pulley is 300 RPM. The coefficient of friction is given as 0.4 and the maximum allowable belt tension is 445 newtons. In this particular case, we're asked to ignore the centrifugal tension effects. Answer is shown in the bracket here. If you think you can attempt this question without further assistance, I'd encourage you to do so. But I'll show you the full worked solution on the following slides. So example 3, here's the beginning of the solution. As always, we initially extract the information from the question. The pulley diameter is 1 meter, so capital D, 1 meter here. That means, of course, the radius, capital R shown here, is half of the pulley diameter, so 0.5 meters. The angle of contact is 120 degrees, so that's really the angle of lap, theta 120 degrees. That'll be this angle here. That's the actual contact of the belt with the pulley. And I've also converted that into radians, so 120 degrees multiplied by pi divided by 180. So 2 pi divided by 3 radians. The coefficient of friction stated in the question is 0.4. So mu here, 0.4. And the maximum allowable belt tension is 445 newtons. So I've called that TT here, is 445 newtons. The speed or the angle of velocity of the pulley is 300 RPM. So capital omega here, 300 revs per minute. Here's a slide of the summary of formulae relating to flat belt drives we've reviewed in both parts 1 and parts 2 of this lecture series. The question wants us to find the power transmitted. We're given in the question the coefficient of friction, the maximum belt tension, the geometry and the angular velocity. So considering the power equations in our list of formulae here, the first one we derived in part 1 requires us to know the slack side tension, which we do not know, and the second power equation we derived in this presentation requires the belt maximum tension, Tt, the friction coefficient and the angle of lap, all of which we are given explicitly in the question, and it also requires the linear velocity, which we can calculate from the information given in the question. We're asked to ignore centrifugal effects, and this equation doesn't account for the Tc value. So this is the equation I'll be using in the solution of example 3. So example 3, solution continued. In the question we were given the angular velocity of 300 rpm. We'll need to convert that into an angular velocity in terms of radians per second, so lowercase omega here. 300 multiplied by 2 pi divided by 60, so that's 10 pi radians per second, the exact value, or to 4 significant figures, that's 31.14 radians per second. The linear velocity v we calculate from omega multiplied by r. We have our omega value above. We calculated r previously, it's 0.5 meters. So the linear velocity can be written exactly as 5 pi meters per second, or again to 4 significant figures, 15.71 meters per second. We can now calculate the power transmitted, ignoring centrifugal effects. So here's the formula, and we now simply insert the values for the maximum belt tension Tt, for mu, and for the angle of lap. And we just calculated the linear velocity above, it's 5 pi meters per second. I'll let you work through the arithmetic here. So essentially the maximum power that can be transmitted in this situation is approximately 3.97 kilowatts. And we've ignored the centrifugal effects here. Example 4. In part A, we're asked to calculate the power that can be transmitted by a flat belt driven at high speed and having the following characteristics. The belt dimensions, 100 millimeters width, 5 millimeters thick. The density of the belt material is 1,000 kilograms per meter cubed. The maximum stress in the belt is not to exceed 1.5 megapascals. The angle of lap on the smaller pulley is 120 degrees. The coefficient of friction is 0.3. And the centrifugal tension, Tc, is 10% of the maximum belt tension, Tt. So in a moment we'll have to choose the appropriate equation from the list of equations in our summary, and given the information we'll have to calculate the maximum power that can be transmitted, accounting for centrifugal effects. In part B, we're asked to draw graphs of transmitted power against linear belt velocity and for power against the Tc divided by Tt ratio. From this we have to clearly state the speed of the belt when transmitting the maximum power. So we'll read that information directly from the graph. Part C, so we have to state at what conditions the maximum power output can occur. And part D, we have to calculate the maximum power that can be transmitted. So in part A, we're going to calculate the power that is transmitted. In part D, we will calculate the maximum possible power that can be transmitted. The answers to the various parts of example 4 are stated in the bracket here. Part A, part B, part C, and part D. If you feel you want to attempt this question without further assistance, then you can start the presentation and attempt it now, but I'm going to show you the full work solution, including the various graphs, on the following slides. So again, here's our summary of formulae relating to flat belt drives, and we're again asked to find the power transmitted, accounting for CF effects, So although there are 3 power equations stated in this listing, there's only one that contains the centrifugal force effect, the TC value. So this is the equation we'll be using. We will need to find the maximum tension, TT. We will need to calculate the value of TC and also the linear velocity V from the information given in the question. But we're given the friction coefficient and the angle of lap in the question, so we have that information. We just need to be careful with the units we're using. Note the formula to calculate TC is shown here. It's mv squared. Remember that m is the mass per unit length. So example 4, here's the commencement of the solution. Extracting the information from the question, we're given the belt dimensions. They were 100 millimeters width, so that's 0.1 meters width, and 5 millimeters thickness, so that's 0.005 meters. We can calculate the area of our rectangular belt. So the area of the rectangular belt is 0.0005 meters squared. We're given the belt density, symbol rho here, it's 1,000 kilograms per meter cubed. So to calculate the mass per meter, lowercase m here, that we'll need in our calculations, that's the density multiplied by the area of the belt. So that's 1,000 multiplied by 0.0005. So that's 0.5 kilograms per meter. The maximum allowable belt stress given in the question, that's symbol sigma here, is 1.5 megapascals, so that's 1.5 times 10 to the 6 newtons per meter squared. Remember, 1 pascal is 1 newton per meter squared. The minimum angle of lap given in the question is theta, so that's 120 degrees multiplied by 2 pi divided by 360, so that's 2 pi upon 3 radians, or 2.094 radians, to 4 significant figures. The friction coefficient mu is 0.3, and the question states that the centrifugal tension TC is 10% of the maximum belt tension TT. So the mathematical notation TC is equal to 0.1 TT. We need to calculate the TT in a moment. So example 4, solution continued. So let's calculate the maximum allowable belt tension. So knowing that the allowable tensile stress is TT divided by the cross-sectional area of the belt, then rearranging the tight side tension TT is the stress multiplied by the area of the belt. Inserting the values, the maximum belt tension is 750 newtons. We're informed that the centrifugal tension, TC, is 0.1 multiplied by TT. That evaluates to 75 newtons. Now to calculate the linear belt speed, that's symbol V, we know from our summary of formulae that TC is equal to the mass per unit length multiplied by V squared. That's in our formula sheet here. So rearranging for the velocity V, dividing both sides by m and then square rooting, V is equal to the square root of TC divided by m. Inserting the values, the linear velocity of the belt is 12.25 meters per second. Example 4, solution continued. So now we're going to calculate the power transmitted P, accounting for CF effects. Here's the power equation. Inserting the values for the maximum belt tension, TT, the value of TC, our friction coefficient, our angle of lap, and the linear velocity, we can evaluate the power transmitted at 3,857 watts. So that's part A of example 4 completed. Example 4, solution continued. This is now part B. In part B, we're asked to plot a graph of the power transmitted against the linear velocity, so P against V. On this slide, I've stated the appropriate information extracted from the question using the power transmitted equation here, extracted from our formulae sheet, where the V, of course, is belt linear velocity. Essentially, I form this equation for power transmitted P as a function of V. So all I will do now is put values of V into the equation and calculate values of P, and then I can plot my P against V. I'll show you the graph on the next slide. Here's example 4 solution for part B continued, and the question wanted us to determine at what speed the maximum power was transmitted. So from our graph here, this looks like the location of maximum power on our vertical axis, about 5,200 watts approximately, and reading off on the horizontal axis, that seems to be approximately 22.5 meters per second. So that's the estimate from our graphical solution for the belt linear velocity when maximum power has been achieved. Example 4 solution, part B continued here. The question also wanted us to plot power as a function of the centrifugal tension, Tc. So again, a similar approach as before. I've extracted the information from the question here, but this time I've generated my power equation in terms of Tc. So power is a function of Tc here. And now I'm going to plot power against the ratio of Tc upon Tt, which is what the question required. I'll show you the graph on the next slide. So example 4, solution continued for part B. Here for reference is my power equation, this time a function of Tc. Again, I've used a spreadsheet to calculate my values. Here's the power, P in watts, and here is the ratio of Tc divided by Tt. That's on a horizontal axis. So plotting the values, power on the vertical axis in watts, and here's our ratio of Tc divided by Tt on the horizontal axis. The question asks us to state what the condition is for maximum power from this graph, and essentially, and by inspection of the graph, the maximum power transmitted, again around about 5,200 watts, occurs at a Tc upon Tt ratio of what seems to be about 1/3. So from the graph, the maximum power output occurs when the ratio of Tc to Tt is equal to 1/3. So in other words, when the centrifugal tension reaches 1/3 of the maximum belt tension, we generate the maximum power condition. That was part C of our solution. So finally, for example 4 in the solution, this is part D now. The question wants us to calculate what would be the maximum power that can be transmitted by this system, assuming we can achieve the Tc upon Tt of 1/3. So for reference, I've just repeated the original calculation for part A, where we calculated the maximum power based on the original conditions of the belt drive given in the question. But now we're going to use the relationship that Tc is 1/3 of Tt. So for the maximum power transmission, Tc is 1/3 of Tt. So that's 750 divided by 3. So Tc is 250 newtons. We can now calculate the linear belt speed for maximum power transmission from Tc is equal to m multiplied by v squared. We can rearrange for v and insert in the values for Tc and the mass per meter. We can evaluate the belt's linear velocity for maximum power transmission, which is a very fast linear velocity here. Note for reference, this linear belt velocity equates to a speed of 80.5 kilometers an hour, which is obviously excessive, so not practically achievable. So this maximum power calculation is purely a theoretical condition. So now calculating the maximum power can be transmitted, Pmax, I've labelled it here, using the formula for maximum power we derived previously, but now inserting the Tc value of 250 newtons and the belt linear velocity of 22.36 meters per second, we find that the maximum power that can be transmitted is 5,215 watts. So that's effectively a theoretical value based on optimum conditions being achieved. Let's consider maximum power transmission. We're going to use an analytical solution here to confirm the values we tentatively found with our graphical solution on the previous slides. So for maximum power transmitted, the differential of equation 14, shown here for convenience, that is differentiating power with respect to velocity, dp by dv, must be equated to 0, because that's when the rate of change of power with respect to velocity is 0. In other words, we'll have a maximum or a minimum value, what we've referred to as turning points in a previous lecture related to differential calculus. So differentiating equation 14 with respect to velocity and equate to 0 for a turning point. So we're going to find dp by dv and equate it to 0, and then solve the resulting equation. So differentiating our power equation, shown here, with respect to velocity and equating it to 0. Maximum power transmission proof continued. Just repeated the equation from the previous slide here for reference. So firstly we'll divide the equation throughout by the bracket of 1 minus e to the negative mu theta, because that's a constant effectively. So that simplifies this expression, d by dv of tt minus tc multiplied by v. All that's happened on the next line, I've simply expanded the bracket, so tt multiplied by v minus tc multiplied by v. Noting from equation 11 we derived previously, the centrifugal tension Tc is equal to mv squared. So we can now replace Tc here with mv squared. And note that produces mv cubed here, because we have a v multiplied by a v squared. That produces the v cubed. And now we're ready to differentiate this equation because it's in standard form. The power transmission proof continued. Just repeated this line from the previous slide. We now need to differentiate the equation. Notice that both the TTV term and the mv cubed term are actually in standard form. They're both actually of the form ax to the n. In the first term, a is the tt, x is the v, and n is 1. In the second term, the a is the m, the x is the v, and the n is the 3. So if we use our standard form for the differential of ax to the n and follow the pattern, we will find that ttv differentiates to tt, and the negative mv cubed differentiates to negative 3mv squared. Just note for reference, if we now calculate the second differential, in other words find d2p by dv squared, if we differentiate this line now, the tt would disappear from the equation, and the negative 3mv squared would become negative 6mv. Note this is a negative value, so that actually produces a maximum. Again, if you refer to our previous lecture on turning points, when the second differential has a negative value, we have found a maximum. So in this context, that's maximum power transmission. Now simply rearranging the equation from above, in other words, adding 3mv squared to both sides and then dividing by 3, we can write mv squared is equal to tt divided by 3. We know that mv squared is actually tc, so therefore we can write tc is equal to tt divided by 3. Call that equation 16 for reference. So in other words, from our graph, we could estimate that the maximum power occurred when Tc divided by Tt was a third. Referring back to this graph here, maximum power occurred when the ratio of Tc divided by Tt was approximately a third. And if we now substitute equation 16 above into equation 14 on our previous slide, shown here for reference, We can write this following expression for maximum power. P is equal to Tt minus Tt upon 3 multiplied by, in brackets, 1 minus e to the negative mu theta multiplied by linear velocity v. And that equation can be further simplified because Tt minus a third of Tt is actually 2/3 of Tt. So we can rewrite the equation in the condensed format as shown in equation 17. So now we have a formula for the maximum possible power that can be transmitted by a belt drive system should we need to calculate that. Just a note here pertaining to the theoretical maximum power condition. So from the above discussion related to our graphical and analytical solutions, maximum power is transmitted when the centrifugal tension Tc is equal to a third of the maximum belt tension Tt. However, it's important to note this is only true if the maximum allowable tension in the belt is induced, which is a condition seldom achieved or maintained in practice. Hence, this calculation for maximum power condition is really only applicable for providing a guide as to the upper limit of maximum power output from a friction belt drive system. We'll finish this part of the presentation by considering some belt drive design requirements. This is purely for reference and relates to practical considerations associated with friction belt drive design and installation. So when designing a belt drive and the associated pulley arrangements for a specific use, and to ensure correct installation of the drive, there are several important factors that are required to be considered. The following list of basic data for the drive selection must be considered and stated. Item 1. The rated power of the drive-in or other what term prime movers. 2. The service factor, which is dependent on the time in use, the operating environment, and the type of duty to be performed by the friction drive system. Item 3. The belt power rating. Item 4. The belt length. Item 5. The size of the drive-in and driven pulleys and the center distance between the pulleys. Item 6. Correction factors for belt length and lap angle on the smaller pulley. Item 7. The number of belts to be used in the drive configuration. And item 8. The initial belt tension. And finally, for reference, there are lots of specialist manufacturers of belts and belt drive systems that have specialist knowledge and various information, charts, tables, etc. that you can access to actually help you design belt drive systems. So it's important to refer to these specialist manufacturers when considering the use design of friction belt drive systems. So here's the bibliography used to help generate this presentation. I hope this part 2 of the friction belt drive presentation has been of interest to you and look forward to seeing you for part 3. Thank you for viewing.